Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 15. F Programming Language Design. The Syntax of Intention. Remember the language we are learning. There is one field, phi, the holophase. One continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We stand at the threshold of 10.3, programming. In Book 10.1, we learn to read phi. In Book 10.2, we learn to measure and mirror it. Now, we learn to speak to it. We leave the observation deck and enter the control console. Imagine a vast, quiet room with a single, curved interface of light. Before you is not a keyboard, but an intention engine. Your tools are not commands to machines, but phrases in the mother tongue of physics. Your goal is not to manipulate bits, but to compose coherent patterns in phi itself. This is the skill of the programmer. You are learning to write instructions that the universe, when asked politely through our foundries, might choose to obey. This part is the very first lesson. We learn the syntax of intention. We design the language. Scene: the composer's studio. Picture a master composer at a grand piano. But this piano's keys don't play notes of sound. They play notes of change. One key might initiate a gentle gradient in phi. Another might impose a rhythmic pulse of omega. A chord might weave a topological knot. The composer's score is not sheet music, but a program, a sequence of grammatical phrases that describe a desired tapestry of phi in time and space. Our puzzle is simple, yet profound. What should that programming language look like? How do we design a set of words and rules, a syntax, that a human can write, that a computer can compile into low-level physics operations, and that reliably produces a stable, coherent phi pattern in the digital twin? We are designing the interface between human thought and physical law. The language role, from intention to executable phi structure. This part teaches a programming skill. Specifically, it is the skill of abstracting intention into phi grammatical constructs. We are building the bridge between "I want a standing wave here" and the precise sequence of field manipulations that creates one, without causing destructive interference or instability. Our core question about phi is: how do we encode the human desired pattern into a sequence of permissible operations on the phi field such that the resulting structure is grammatically correct and dynamically coherent? We are not yet running the program in a physical foundry. We are writing it, and our first test is whether it compiles and runs cleanly in the digital twin, our sacred sandbox. The anchor image, the control console. Throughout this part, we will return to the image of the control console. It is not a chaotic panel of switches. It is a minimalist, intentional interface. It has primitive knobs and levers. For basic operations, seed, impose, inject, apply. Sequencing timeline. For ordering operations in time, loops, conditionals. Modular base. For inserting pre-written routines, functions, libraries. Coherence dashboard. Constantly displaying the predicted grammatical health and resource budget of the program being written. This console is where we practice speaking before we act. The coherence selection principle in programming. In episode 10, engineering is coherence management. In programming, this becomes law. Constructive resonance, alignment, in a program means its instructions are mutually consistent and produce a stable, persistent phi pattern. The clauses it writes do not conflict, they harmonize. Destructive resonance, dissonance, means the instructions conflict, violate a core constraint, or produce an unstable, self-canceling, or chaotic pattern that quickly decays or fractures. Therefore, our programming mantra: if coherence breaks, we stop. If coherence returns, we continue. We do not run a program that compiles with warnings of constraint violation. We do not ignore an unstable output in the twin. We stop, debug, and rewrite until coherence is restored. The core mechanisms, primitives and control structures. A phi programming language must have primitives, the atomic verbs of creation, and control structures, the grammar for combining them. 1. Primitives, the atomic verbs. These map directly to fundamental operations on a phi field. Seed phi, value, region, inserts the phi field in a defined spatial region to a specific phase value. This is the let there be light command, but for phase. Time echo sets the initial condition. Space echo defines the spatial footprint. Motion echo implicitly defines potential gradients that may cause drift. Impose Xiaomi background locks the phi field or its derivative, like gradient, at a spatial boundary to a specific condition. For example, fixed phase, periodic, zero gradient. This defines the walls of your experiment. Time echo. The condition persists for the duration. Space echo defines the spatial limit. Motion echo constrains flows at the edges. Inject defect, type, charge, location. Creates a topological defect, a vortex, a monopole, a dislocation, with the specified integer charge at a point or along a line. This is how you tie a knot in the phi field. The language must enforce that charge is an integer. For example, charge equals 1 or minus 2. Trying to inject charge equals 0.5 is syntactically and physically nonsense. Apply constructor, constraint name, strength, region. Advocates a specific physical clause from 10.1.2's library in a region. For example, apply constraining, wave equation, c equals 1.0, region so far, would make the phi field obey wave dynamics with a certain speed. Apply constructor, diffusion, d equals 0.1, region equals fluid, would add dissipation. This is how you set the rules of the game for different parts of your canvas. 2. Control structures, the grammar of combination. These dictate the flow of execution. Loops for iteration, for time step in range total steps, or while coherence threshold. This allows for iterative processes, like gradually ramping up a driving force or letting a pattern relax to equilibrium. Conditionals for constraint checking. If measure defect charge lorsk target charge, rollback. This allows the program to check the state of the phi field and make decisions, enabling adaptive control and safety rollbacks. Modularization, functions and libraries. Def, create vortex mixing, separation. You can package common sequences, like creating a stable vortex-anti-vortex pair, into reusable functions. Libraries can contain whole suites of functions for standard tasks. Import patternslib, then patternslib.shagonal lattice, spacing equals 0.5. The coherence criterion, grammatical consistency. Our coherence criterion for a valid phi program is strict. A valid phi program must be grammatically consistent. Its instructions must not violate core phi constraints at the syntactic level. The language itself is our first line of defense. It should be designed to prevent syntactically incoherent commands. This is not just good practice, it's a safety rail. The compiler should inject defect, charge equals 0.5 at compile time. It should flag apply a braze incompressible flow in a region where an apply constructor phase separation is already active, if those constraints are known to be mathematically incompatible. It should require that every seed phi has a defined region, and every imposed conserve reference is a valid boundary. A program that passes this grammatical check is syntactically coherent. It doesn't mean it will work as intended, but it means it isn't nonsense from the outset. The dissonance indicator, semantic nonsense. The greater challenge is semantic coherence. This is our primary dissonance indicator. A program that compiles is syntactically fine, but produces wildly unstable or physically impossible outputs in the twin, indicates the language allows expressions that are syntactically valid but semantically nonsensical in phi space. For example, consider this program. Seed phi, 0, region equals circle, radius equals 1. Inject underscore defect, type equals vortex, charge equals +1, location equals 0, 0. Inject underscore defect, types equals vortex, charge equals +1, location equals 0.1, 0.1. Another same sign vortex very close, apply container, xy model relaxation, t equals 0.01, run for stems equals 1000. Syntactically, this is perfect, but semantically, it's asking for trouble. Two same sign vortices in the xy model repel each other fiercely. Placing them extremely close in a relaxing system will cause a violent, unstable motion that likely destroys the intended pattern. The twin will show chaos or rapid, unpredictable motion. The language cannot prevent this entirely. It's a logically valid, if foolish, intention. But a well-designed language could include warnings or semantic analyzers that detect high-stress configurations and suggest revisions. The ultimate test is the twin. Unstable output equals semantic dissonance. Time to rewrite. The coherence budget and safety rail. Mandatory declarations. Before we even run in the twin, we have a coherence budget for the program itself. 1. Computational budget. Simulating the program's effect has a cost. The language must include mandatory resource declarations. Requires max grep points, coherence length, but we place them too close. We stop and rewrite. Runtime fail. The program compiles and runs, but the twin output is wrong. Only 3 defects appear, a pair annihilated. Or they are in the wrong places. Or the whole pattern explodes into chaotic phase slips. This is semantic dissonance. We roll back. We do not proceed to physical foundry. We enter debugging. 10, 3, 2. The prediction spine, what a good language delivers. A well-designed phi programming language yields a clear prediction spine. 1. Identical outputs. A program written in this language will produce identical outputs when run on identical, calibrated digital twins. This is the foundation of reproducibility. The language eliminates ambiguity. 2. Code-to-action correlation. The complexity of a program, in lines of code or in primitive operations, will correlate with the physical action cost of its execution in the twin. A simple gradient, seed fins with a ramp, has low action. A complex, knotted defect network has high action. The language makes this cost conceptually transparent. 3. Modularity generalizes. Modular, well-structured programs using functions, libraries, will be easier to debug and will generalize more reliably than monolithic scripts. A function make solon that works for one system can, with careful parameterization, often work for another. Spaghetti code is fragile and unpredictable. Falsifiability, the limits of abstraction. Our falsifiability threads keep us honest about the language itself. If, despite exhaustive effort, no high-level language can be designed that both significantly improves human productivity and reliably compiles to stable twin executions, then phi programming may be inherently too low-level for useful abstraction. Perhaps every desired pattern requires hand-tuning low-level physics parameters. This would mean our dream of intuitive reality programming is flawed. We are stuck as machine code writers for the universe. If the language, once designed, cannot express a physically possible phi pattern that we know how to create through other means, for example, through direct manual manipulation in a foundry, then the language is incomplete. It has missing primitives or control structures. This is a design failure we must correct. These falsifiers ensure our language serves reality, not the other way around. Triunity in language design. The language itself reflects triunity. Time echo, control structures. Loops and conditionals handle sequence, duration, and rhythm. A for loop over time steps creates a temporal process. Space echo, primitives and regions. Seed phi, impose budget. Spatial parameters in inject defect. These all define texture and spatial structure. Motion echo, dynamics from constraints. The apply constructor primitive is the key. It imports the dynamical laws, wave, diffusion, flow, that generate motion and flow from the interplay of the initialized space and time structures. A complete program weaves all three echoes into a single coherent intention. Lanterns across scales, the syntax of creation. This language isn't for one thing. It's a universal syntax for intention. Near scale, material design. Program a metamaterial. Seed phi with a periodic pattern. Apply conditionals elastic relaxation. Run for until equilibrium. The resulting frozen phi map defines the atomic or metastructure that gives rise to exotic optical or acoustic properties. You've just programmed a material. Middle scale, robotic swarm coordination. Imagine each robot has a local phi value, its phase. A program broadcasts apply condition, sync to Glover omega, target freedom 1 Hz. The swarm self-organizes into synchronous motion. Another command, inject defect, type equals phase wall, line equals, could create a virtual boundary the swarm won't cross. You're programming collective behavior through field dynamics. In a planetary twin, you could write a program to test the geoengineering idea. Apply controlled albedo instead, region equals Arctic, strength equals 0.05. The language allows you to cleanly express the intervention, and the twin shows you the complex, cascading consequences in the climate system before you ever touch the real atmosphere. The ethics of syntax, constraining power at the source. The ethics of programming in episode 10 is operational discipline. Here, it manifests as constraining power at the source, in the language design itself. 1. Consent by syntax. The language's mandatory declarations, requires, declares, force the programmer to explicitly state the scope and resource cost of their intention. This is a form of accountability burned into the code. 2. Containment by compiler. The compiler that enforces integer charges and budget limits is a containment mechanism. It prevents impossible or overwhelmingly dangerous ideas from ever reaching the simulation stage. 3. Reversibility by structure. Well-structured modular programs are easier to reverse. A function, create parent, should have a corresponding dissipate parent or rollback to rebrotate. The language can encourage or even mandate parent creation destruction routines for certain primitives. The language designer holds immense ethical power. They decide what is expressible. By making it syntactically impossible to write inject defect charge equals 0.5, they bake a fundamental law of physics, topological charge quantization, into the very tool of creation. Power is not just in what you can do, but in what the system prevents you from even trying. The recognition skill, seeing programmable structure. You know you need this skill when you look at a natural or design pattern and think, that looks like the output of a simple algorithm. When you see a honeycomb, you recognize a potential hexagonal lattice clause. When you see a spiral galaxy in a simulation, you might hypothesize a seed phi and apply contractor process. When you see a heartbeat, you see a limit psi oscillator pacemaker. If you find yourself wanting to not just describe, but prescribe a pattern, to say, make it thus, you have entered the programmer's mindset. The first step is to reach for the syntax that can capture your intention. The master tree location. This part 10.3.1 is a crucial branch on the master tree. It depends entirely on the roots of 10.1.2, the clause library. Our primitives need to map to known physics. And 10.2.5, the digital twin, our compiler target and testing ground. It is the first green shoot of Book 10.3. It enables the next branches. Debugging, 10.3.2. What do we do when the twin output is wrong? Advanced control structures, 10.3.3. And ultimately, compilation, 10.3.4, turning this high-level code into instructions for a real foundry. This part provides the source code. Return to the phi. Let us zoom out. We are designing a language to talk about a single field and its changes. Every primitive is a permitted manipulation of phi. Every control structure is a rule for combining those manipulations in time and space. The coherence criteria are nothing but the grammatical rules of phi itself, reflected upwards into our symbols. The universe runs one endless coherent program, the unfolding of phi according to its constraint clauses. We are learning to write tiny local subroutines that, if they are coherent with the main program, can be spliced in without crashing the system. This is the beginning of true dialogue, not just listening, but forming a grammatically correct reply. Zenodo and the equations of the language. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There, you will find the scientific papers that this audio journey is built on. The papers formalize the language semantics, how inject defect maps to a specific boundary condition in a partial differential equation solver, how apply struction links to equation terms, the type theory behind the compiler's constraint checking system, and the information theoretic proofs showing that a well-designed language can compress complex physical intentions into efficient code without loss of essential meaning. So, picture yourself at the control console. The interface glows softly. You begin to type, or perhaps to speak, your first program. Program simple wave requires domain size equals 1010, requires simulation steps equals 500, contingency phi value equals 0, region so far in, impose Qiaomi condition equals periodic, boundary equals no, apply config, wave equation, c equals 1.0, region Alex is ill, inject defect, binobar equals source, frequency equals 0.5, location equals 5, duration equals 100, e. You hit compile, the console lights up green. Syntax okay, budgets satisfied. You hit run in twin. On the main display, the digital twin awakens. From a point at 5, a perfect, expanding circular wavefront emanates, washing across the periodic domain. It is beautiful, stable, and exactly what you asked for. You have just written your first sentence in the universe's native tongue. You have used the syntax of intention. This is part 10.3.1, Phi Programming Language Design. It is the foundation of Book 10.3, the moment we move from describing what is to prescribing what could be. In our next session, we will face the inevitable truth. Our first drafts are flawed. The wave might be too weak. The grid of defects might drift. We will learn the sacred skill of debugging. We will learn to listen to the twin's feedback, to interpret error residuals not as failure, but as the universe's gentle correction of our poor grammar. We will learn to refine our speech until it is coherent. Remember, one field, phi, with its infinite echoes. We have just picked up the pen. Our conversation is beginning. Salam, and peace be upon you.